How to analyze stability for real-world control systems. Have you ever wondered how engineers ensure that control systems work smoothly without unexpected behavior? Analyzing stability is the key. In electrical engineering, stability analysis is essential for systems like power grids, motor controls, and communication networks. It helps us determine if a system can maintain its performance over time without oscillating or diverging. To start, a control system is considered stable if all the poles of its closed-loop transfer function are located in the left half of the complex S-plane. This means they have negative real parts. If poles are found in the right half-plane or on the imaginary axis, the system is unstable or only marginally stable. There are several methods to analyze stability, ranging from algebraic techniques to graphical and frequency domain approaches. One popular method is the Routh-Hurwitz Stability Criterion. This algebraic technique involves creating a Routh array from the coefficients of the system's characteristic equation. If all elements in the first column of this array have the same sign, the system is stable. If there are sign changes, it indicates instability. Another method is the Root Locus Technique. This graphical approach shows how the locations of closed-loop poles change in the S-plane as a system parameter, usually gain, varies. By plotting these trajectories, engineers can identify the range of parameter values that keep the poles in the stable left half-plane. This method is particularly useful for controller design. The Nyquist Stability Criterion is a frequency domain method that analyzes the open-loop transfer function. By plotting its response in the complex plane as frequency changes, engineers can examine the Nyquist plot for encirclements of the critical point. The number of counterclockwise encirclements must match the number of open-loop poles in the right half-plane for stability. Bode plot analysis is another valuable tool. Bode plots display the magnitude and phase of a system's frequency response. By looking at gain margin and phase margin, engineers can assess how much gain or phase variation the system can handle before becoming unstable. These margins provide important measures of stability and robustness. In practice, engineers often combine these methods. For instance, the Routh-Hurwitz criterion can quickly check stability for a set of parameters, while root, locus, and frequency domain methods help with controller tuning and robustness analysis. Real-world control systems can also have nonlinearities, time delays, and varying parameters. While the methods mentioned primarily apply to linear models, engineers use them as starting points and validate stability through simulations and experimental testing. Applications of stability analysis are widespread. In power systems, it ensures that generators and loads remain synchronized during disturbances. In motor speed control, it helps maintain desired speeds without oscillations. In communication systems, it stabilizes feedback loops in amplifiers and filters. By using mathematical criteria like Routh-Hurwitz, graphical tools like Root Locus, and frequency domain techniques such as Nyquist and Bode plots, engineers can verify that all system poles stay in stable regions under expected operating conditions. This layered approach balances theoretical rigor with practical design needs, ensuring that control systems perform reliably in the real world.